Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Alfa Firdaus. I am student at University of Indonesia. Before I start my presentation, I want to apologize to you all because I couldn't make a video presentation like the example that we know due to my limited equipment that I have. The title of this research is Model Predictive Control Design of Pressure Swing Distillation for Methanol-C separation. My talk is divided into 4 sections. They are Introduction, Methodology, Result and Discussion, and the last is Conclusion. Pressure Swing Distillation, or we can call PFD, is a common unit that is used for separating azeotropic mixture. PFD is used when the azeotropic separation is affected by pressure. Third amyl-methyl ether production is one of the chemical processes that can use PFD for separating the excess reactants. In this research, the PFD scheme is taken from Leuben's paper. In that paper, he talked about plan-wide control of tamine production, but in this paper, we just focus to the PFD system. The PFD system consists of 2 columns of distillation. They are C1 and C2 column. This unit the duty of this unit is to separate the excess reactant from reactive distillation. The excess reactant consists of methanol and C5. To achieve the desired specification product from the separation process, a controller is needed to control the operating condition of the units. The control system in this unit was PI control, but as we know, PI control has some drawbacks. So in this paper, Model Predictive Control, or MPC, which is one of the advanced control, was used to improve the control performance when handling any kind of disturbances. The goal of this research is to implement MPC in the PFD process in order to improve the control performance. In this study, the performance of MPC and PI will be compared based on the integral square of error of MPC and PI against set point change and disturbance respectively. In this research, we use HYSYS to simulate the process and also the control system. PID control is tuned by auto-tune that is available in HYSYS. So this is the PFD scan in HYSYS. All temperature and pressure controller use PI control, but for liquid level use P only controller. After that, we make a process reaction curve. This curve shows interaction between input and output in every controller. Based on this curve, we can make a model that is used to design a MPC. Based on that curve, we can build a simple first order plus that time or FOPDT model. This model is very crucial when we design the MPC because it will affect the accuracy of the MPC to make a control action. After that, we tune the MPC parameters to get an optimum performance and to compare which controller give a better performance. We did set point tracking tests and disturbance rejection tests. Set point tracking is performed to see the dynamic responses when the controller tracks a new set point. As we can see here, for pressure and temperature for column C1, the result is quite similar in contrast with a level controller. It is very makes sense because all level controllers in P mode cannot reach the desired value because of the characteristic of the P controller, which cannot produce the zero offset. And this is the result for C2 column. I think the analogy is the same. The result is quite the same for the column C1. To make sure which controller has a better performance, we can look at this table. This table contains the IFE values of each controller, where the smaller IFE values, the better the performance of the controller. Here MPC has a smaller IFE value than PI controller. So based on that value, we can conclude that MPC has a better performance than PI control in set point tracking test. So now for disturbance rejection. This disturbance rejection is performed by increasing 10% feed flow rate in column C1, and then we will see the controller responses in order to make the process variable back to the desired value. At a glance, we can see that MPC is better than PI because it has a smaller overshoot, and then MPC have a stable performance because it can set back the process value to the set point. So this is for the column C2, but the result again is similar with column C1. To make sure which controller give a better performance, we can see at this table. Based on this table, the performance of MPC is better than PI because it has smaller value of IFE. So for the conclusion, in this study, an alternative control type has been studied. MPC provides satisfactory control when dealing with set point change and disturbance tests. The comparison between MPC and PI clearly shows that the MPC has better responses than the PI controller. MPC produces around 21 up to 52% improvement in set point change tests compared to controllers. A disturbance of 10% increases in the feed flow rate of column C1 was done to see the controller responses to reduce the deviation between the process variable and set point value. Around 5 until 52% improvement was generated by MPC compared to the PI controller. So this is the reference. So that's all from me. I hope this research can be useful for all of you. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.